Good afternoon, everybody. Welcome to the next IETS TCP webinar. I'm very happy that you join us this afternoon. We are talking today about digitalization and AI for energy efficiency. And as usual in the webinar series that we are working on with the IEA, within the IEA program, we have a lot of projects and directly from the research. So we will have four project presentations that are working on the very interesting question and intersection on digitalization and AI for energy efficiency. I think it's a topic that is very current and a lot of people are talking about. And it's really the question, how can we make digitalization and AI use for the benefit of the energy transition and the industrial transformation? We're talking a lot about the usage of or the energy demand of AI and digitalization. And I think it's very important to counterbalance this discussion with what can these approaches bring us actually for making the transformation itself. So we have some very hands-on research projects here that bring us a bit closer to the topic of understanding, how can we bring this to the industry, how within first pilot cases, etc., how is it already applied? So I'm very much looking forward to guiding you through this afternoon. My name is Heike Brugger. I'm managing director at IRES in Germany. That's the Institute for Resource Efficiency and Energy Strategies. And amongst others, we are doing the accompanying research for the German energy research program, concentrating on industry. On the industry sector. So we have many speakers today for you, which is super exciting. We start with a brief introduction from the IETS Secretariat that you learn a bit, those who are not familiar with the IETS and found their way here anyways, to learn a bit more what this is about, what the programs are about. Then we have a direct introduction into the specific task 18 that is working on digitalization and artificial intelligence and related technologies within the working program. And then we have 4 project presentations that are working with AI and digitalization for the industry sector on very different levels. So we're starting with the foundational models in the energy sector. We have some really applied cases where the projects are working with demonstration projects in different types of industries, you get an impression of what AI can really do here. And we have 20 minutes per presentation for each of the projects. And you have also the chance, of course, to ask some questions. We have here, you might see it above, we have the Q&A section. So please, if you have questions, put them in the Q&A section. Then this is the advantage. We can select a bit the questions, but also the speakers might have the chance, in case in the 5 minutes we don't have the chance to answer, they have the chance to respond to you in a written way. So if you have any technical questions, you can use the chat function. If you have content-related questions to the speakers, please use the Q&A section. And then we hope we can, despite the very full-packed afternoon, we can answer a lot of questions and give you a deep dive into the current research on AI and its way for the industrial transformation. I'm very excited to present the speakers to you. We start with Ellen Svensson from the IETS Secretariat, who will give us a quick introduction on the TCP program. Ellen, the floor is yours.
Thank you. So let's see if I can switch the slides here. No, it doesn't work. So maybe you can switch for me, Heike. Yes. My name is Elin Svensson, and I represent the Secretariat of IETS, Industrial Energy Related Technologies and Systems, which is the program that is hosting this webinar series. In IETS, we have 12 member countries and also sponsor organizations from 5 additional countries. Now I see the wrong slide there. Still, yeah, thank you. The most recent sponsor from Belgium is actually so new that they have not yet been included among the flags that you see here on the first slide. It was confirmed just a few days ago. And then we can move on. So the IETS is a technology collaboration program, a so-called TCP, under the International Energy Agency. The TCPs, they are unique global networks that bring together governments, industries, and leading experts to support energy efficiency and decarbonization. In total, there are about 40 TCPs, but the IETS is the only one with a dedicated focus on industry. And the overall aim of IETS is to strengthen international cooperation on energy savings and greenhouse gas mitigation in industry across a broad range of sectors and from both a technology and a systems perspective. Next slide, please. Our work is organized in so-called tasks, and these are collaborative research and knowledge sharing activities, each focusing on a specific topic. At the moment, we have 9 active tasks covering both technology-oriented and system-oriented aspects of industrial energy transition. And I won't go through each task in detail here, but I want to highlight the breadth of topics, from biorefineries, heat recovery and membrane processes, to electrification, circular economy, climate resilience, drivers and barriers, and process integration. And today's webinar then is connected to task 18, which you will hear more about in a moment. Switch slide, please. Why should you participate in IETS work? Well, you get the opportunity to engage in this international collaboration, to communicate and network directly with leading research groups. And this leads to various synergy effects and opens opportunities for knowledge transfer. You also get access to reports and workshops and webinars that are not open to the public, or get access to them before they are published. Next slide. So how do you participate in a task? The participation is based on so-called task sharing, and this means that you bring your already funded projects and actively contribute through meetings, workshops, and joint activities. So there are no calls or no central funding, but participation is based on your contributions of time and expertise. If you're interested in joining a task, you contact the task manager, your country delegate, or us at the Secretariat. So to join a task, you have to belong to one of the member countries or become a sponsor organization. And we also welcome new member countries. Next slide, please. On the IETS website, you can find more information about all the tasks, about events, publications, and also contact details. A good way to stay updated is to subscribe to our newsletter, and then you'll also receive invitations for this webinar series. And the final slide. Just to say, don't hesitate to contact us and enjoy today's webinar. That's all from me. Thank you.
Thank you so much, Ellen, for the quick introduction. And yeah, I let the slide in for a moment that people can look at the various formats of contacting. And then I'm handing over to Mulut, who is presenting a bit more about the task that was already mentioned, the task we are talking about today on 18 on digitalization and AI and related technologies. Mulut, the floor is yours.
Thank you. Trying to find my presentation. Maybe you can, if you have it, you can share it. Maybe I don't know what's going on here.
Okay, let me quickly move to that. No problem. I will share it. I'm just having to go into a different format, but that's fine. Okay, I think that will do for now. Also, it's not the full screen. I hope that is fine to see.
Oh, okay, you are not in the presentation mode,
Yeah.
Okay.
Let's do it
Thank you
this
very
way.
much. So my name is Mouloud Amazuz. I am the manager of Task 18. And at the same time, I'm representing Canada, Natural Resources Canada, where I am acting as a research manager at the CanMet Energy, which is an energy innovation center. So I'm going to present I would say the achievement of these tasks, because we are close to the end of this task. So next slide, please. So the main objective of this task is to stimulate the adoption of artificial intelligence and digitalization technologies for energy efficiency improvement and GHG emission reduction in the process industry. And to do so, it's through the creation of an international network and infrastructure stakeholder, facilitate joint development of new knowledge and expertise on digitalization, and to support the deployment of digitalization practices in the energy-intensive processes. So we have, in this task, we have 4 subtasks. 3 of them are already completed. So all the final reports, presentations are available on the IETS website. Next slide, please. So for the subtask structure, so the current time frame of this task is we started in 2019, and officially we're supposed to finish in 2027 January. We have 9 member countries and 1 sponsor. So as I mentioned, the first 3 subtasks are already completed. The first one, we started with subtask 1, and the objective of this subtask 1 was to define the needs, the projects, the subtasks to come. So from this subtask number 1, we started 2 subtasks, number 2 and 3, which is of methods and application of digital twins. And the other one is lessons learned and creative value by digitalization. And recently, very recently, we started in January 2025. There is a new subtask number 4, which is about AI methods in industrial energy systems. And we also have a working group. It's mainly composed of industrial partners who are just having meetings to discuss the roadmaps for the implementation of digitalization technologies. Next slide, please. So we have 35 organizations from 9 countries. So it's really interesting that we were able to attract that much organizations. So we have all the names of different organizations here. Next slide, please. So as I mentioned, I'm going mainly to talk about the achievements. So the subtask 4 was about methods and application of digital twins. So I think there is a mistake there, but it's okay. From subtask 1, we started by looking at the basic definition, like lexicon of what is digitalization, what is artificial intelligence, all these kind of definitions. We agreed on some definition, and we have lexicon that is available. We developed it. We made some critical analysis and identified potential common targets area of interest of task participant. We have questionnaire. At that time, we met all the participants to see what is their interest in this task. And as I mentioned, we identified future subtasks at that time. Next slide, please. So for the subtask number 2, we had 16 projects that were shared among different participants to the subtask, all about the methods and the application of digital twins. We developed the roadmap for future R&D and in AI and digital twins. You have the condensed roadmap here if you want to look at it later. And we also have the report if you want to go in more details. It was a very important, we had very important participation organizing sessions on the task in the Energy Future Industry conference in Gothenburg in Sweden. And we also organized several major activities like symposiums and presentation. Next slide, please. Subtask 3 was about lessons learned and created values by digitalization. Here also, we were able to have nine real case studies that were shared and evaluated. We looked at the potential for and the real GHG emission reduction for each of these tasks. We looked at the TRL and so on. We developed the topic sheet summarizing the results of this subtask. We highlighted the transformative impact of digital technologies in industry. And we organized several events and workshops, webinars, subtasks, and so on. Next slide, please. And finally, subtask 4, which is an ongoing subtask, as I mentioned. We started in January 2025. Finish date is December 2026, this year. We have 14 participants from 4 countries. We already started some activities. You see here at the table, we already had the workshop to identify innovative AI methods for industrial energy systems. And as mentioned, we have several activities that just started that we continue working on, like technical, even looking at techno-social consideration of AI, technology roadmap for further development of AI and so on. I think that's it on my side.
Thank you so much, Mulud, for the introduction into the task. I think it's very good to have an overview what is all happening, and it's quite a lot in this task. I would already hand over to Merzat. Merzat is working at RISE, the research institute in Sweden, and will talk us a bit through the foundation models in the energy sector that they are working on. Merzat, will you try sharing the slides yourself? Otherwise,
Yep.
I'll try to figure out that.
No, I will try it. Let me know, please, when you see the slides.
Yeah, looks good.
Okay, perfect. And thank you so much. As Heike mentioned, my name is Merzat Lavasani. I'm a senior researcher in industrial digital transformation at RISE. Very happy to be here. And in the next 20 minutes, I will talk about foundation models, which represent a new way of AI technology, initially general purpose models that learn from vast and diverse data set and can be adapted to numerous tasks through fine-tuning a specialized model. I'm going to talk about the integration potential, the challenges, use cases, and the strategic outlook for foundation model in energy sector. But before we dive in, I hope that you see the slide changes. Before we dive in, context matters. This research was not done in isolation. It was conducted in close collaboration with RISE from Sweden, ZSW from Germany, and IETS from Austria. It was a project led by commissioned by EU Commission and led by Association of European Renewable Energy Research Center, EUREC. I would also say that please note AI assisted in generating the figures today that you are going to see in this presentation, but all the content and data for this research were produced and reviewed by the human research team. So We know energy sector is changing, but what I'm going to talk about today in this presentation is this map that you're seeing. I will start from a brief overview of where we started with AI and digitalization, from isolated system that you see in the left to the vision that we have for a fully integrated system and SOS for digital twins. I will explain foundation models and how they can enable us to realize this vision, and what approaches to develop and how we should adopt which roadmap to take us there. Of course, just one potential. So initially, how we go from isolated left to integrated right, and going to explore the technology, use cases, and the roadmap to get us there. So we know the energy sector is undergoing a fundamental transformation, which is driven by the sustainability goal, economic pressure, technology maturity, and regulations that new mandates requires better reporting and resilience. The expectation is clear. We want enhanced efficiency and reliability. And for that, we have enablers of this system transformation, digitalization that can integrate our isolated system, and AI and at its core that optimizes our processes, machine learning, and digital twins of the next port. But to understand where we are going, we need to understand and where this foundation model fits actually. We must look at where we started. And we started with the general industrial focus when we integrated AI methods for optimizing an energy efficiency in single unit. Then from there, we started to scale out and up and scale out to move to AI methods in integrated system and having system focus level. And from there to digital representation of the assets to do condition monitoring. And now we are walking in the path of process and system through digital twins. But now, what we are trying to go, we are transitioning from these individual twins focusing on asset monitoring and control to digital twin of system, which means we want to allow individual digital twins to communicate and federate within a higher level of integration. And here, the value basically is enabling a holistic optimization of the system, where we can finally understand and predict how the changes in one subsystem affects the entire industrial system or even the landscape. However, if we are connecting these twins, we also require a complex querying for every connection, task, and actions. And here is when foundation models come into our picture. To integrate generalized intelligence into a highly specialized industrial system, potentially, foundation model can facilitate this by helping us querying the system holistically and enhance digital twin creation and calibration, as well as self-correction and adaptation during operational phase. So traditionally, we used to have AI as purpose-built. If we wanted to model for any use cases, such as load forecasting or anomaly detection, we gathered a specialized data set, trained a model for that specific task. And if we then needed another application for another use case, we would start the process over with a new data set and new model. This approach initially means high effort, and every new application that we are creating is also being developed in isolation of those insights that they create. But now shifting to the foundation model, the initial idea is deploying this general purpose model that learns from vast, diverse, and usually multimodal data set. And instead of being a single tool solution, a foundation model can provide a base of generalized intelligence that can be adopted to various tasks through fine-tuning. But why do we need this shift from general to from the specialized ML to foundation model? Because we are facing unprecedented challenges. Grid modernization needs managing aging infrastructure while integrating decentralized resources. Renewable integration requires overcoming the variability of solar and wind to maintain the stability. On the demand side, we must actively balance consumer needs in real time. And of course, we must ensure resilience, security, and protecting our critical infrastructure against physical and cyber threats. This growing complexity and urgent needs calls for investigating options and technologies with potential, like foundation models, that can aid us to pacing up this transformation. But of course, we should not deploy technology for its own sake. So where do we actually start? In the research studies that we have done, we have identified several high potential areas for foundation models integration. In forecasting, they can help us to accurately predict the demand and generation of the energy, while integrating weather and IoT data, for example. For grid optimization, they allow us for real-time control of decentralized grid. Predictive maintenance, of course, they can help us with the sensory data coming from industry to predict and reduce the downtime and extend the asset's life. And of course, the low-hanging fruit that we all are getting to know is knowledge management, because then we can capture the knowledge from logs, reports, and making the decades of operational experience searchable and actionable. Deciding where to start, though, takes us to how to adopt this model into our businesses. We identified 3 general attempts to go forward. We can use existing foundation models, which are great for documentation and coding, such as large language model or ChatGPT that all of us are using, which stands for the general purpose AI. In this sense, we have low computational cost and fast prototyping. The second part that we can go with would be to train the model from scratch, building an FM that is only trained on the own data. This, of course, gives us full control and physics alignment, but it comes with a higher cost and a longer time of return on investments from the computational and energy consumption to competence development. And of course, we always have a hybrid approach. And the hybrid approach, we use a general model that provide us with the baseline of the model that we want, but then we avoid getting into the black box and having distance from the specialized task that we want. So we will have a control on the specialized task while the general part come in. But of course, they would be quite expensive in the term of complexity and require the skills and resources. But as you see in all of these approaches, the decision and which one of these we should take is highly use case based and is a trade-off between the resources, control, and complexity that goes beyond the technology integration only and business and a strategy of organization or ecosystem. The good news is, though, the technology landscape is evolving rapidly. We started with general purpose AI and large language model, but now we are seeing time series specific models for electricity data, and we are even seeing grid specific architecture. But here is the reality check. There is a significant progress, but there are none of these models, at least until 2 months ago, that are fully operational, ready to publicly release in critical capacity. We are in the pilot and validation phase. And even though rapid progress, we need to remain factful about the readiness level of them. But regardless of the path, integration of FM into critical infrastructure for energy sector brings massive responsibility because it amplifies the old and bring new cybersecurity risk. If we have the problem with adversarial attack and data poisoning, now foundation model becomes the single point of failure because it will not be only one model or system that can be affected, but it will be propagated through all the connected systems and models. Also, for example, another one be that a vulnerability of a third party providing the foundation models will easily brings down the whole supply chain. So it is most important to ensure resilience and availability. Trustworthy development must start with security by design, addressing both digital and physical risk. And only after we setting this mindset, we can think about how to move to technically integrating foundation model into any use case or application. In our work, we suggested that the technical integration should follow a logical four-phase path, regardless of the use case or which level or what approach we want to take. And after that, in this way, we can actually meet the minimum prerequisites and then expand and complement based on the specific requirements. For the first and foremost important part is to layering the data foundation. We need to address the heterogeneity and the scale and quality of industrial data that are going to develop the foundation model on. We need to address also secure data pipeline to collect this and curate this to be used by the models. On the second phase, moving to base model training, and developing these FM architectures that are well suited for the specific use cases that we are going to use in energy sector. For example, if it comes to grid, we need to have architecture that's suited for the special temporal grid dynamics. And from that point, we have to move on to application-specific adaptation to ensure that we have a reliable performance for a specific requirements of the application that we are integrating it. We need to fine-tune based on the model that are defining what are the individual systems that we are integrating into. And of course, when it goes for operation, deployment, and real-time operation, these models need to be integrated into existing system, which means we need robust monitoring and performance and trust system in place to ensure that they are acting as they should. But as you see, this complexity means that we cannot have single entity do it all. Success for any activity for foundation model requires an ecosystem of diverse stakeholders contributing to different stage of the technical integration roadmap. Example of that is that we require academia and applied research to drive the fundamental research into new architectures. And we need industry developers, utilities that provide the operational data and lead the deployment stage. Infrastructure provider must offer the necessary computational power, but at the same time, we require regulators to establish safety frameworks and standards and monitoring and auditing system that can ensure what is going on will meet the requirements and meet the vision without sacrificing any of the stakeholders in there, including society. So joint efforts are actually essential to overcome the high cost from the demand to data access and security challenges. So what should we take away to our strategy tomorrow if we are thinking about foundation model? We need proactive preparation for responsible and effective FM integration into energy sector. We should start with domain-specific development and pick low-risk pilots for this purpose, because real-time control at a scale for foundation models just increases the risk that they will not deliver on the premises. FM also are extremely data hungry. Most of the organization usually find that their data isn't as clean or as much as they were thinking about. So we need to audit the data readiness of our organization and collaborators in any application within the value chain. Security comes first. FM cannot be developed and then looked back in the architecture and consider where we should think about integrating more security measure. The time for threat modeling and mitigation plans for FM and AI-specific basically risk is now. And of course, we require collaboration between all the stakeholders, because the cost of developing, deploying, ensuring their secure and trustworthy and responsible operation is really too high to be done in singularity and alone. So the vision for the future of the energy sector is an intelligent, integrated ecosystem. But I want to note something, that our research does not recommend the immediate larger-scale deployment of foundation models into the core grid operation today. Initially, we are building the foundation for the foundation models. We should first master our data readiness and launch high-impact pilots in low-risk areas, which have been already doing their work through the years, and build a security-first AI framework. Then, by prioritizing domain-specific developments and reinforce collaboration, we can actually succeed in realizing the long-term potential that foundation models can bring for us in the digital twin of systems in energy sector. So thank you for your time, and I look forward to our conversation.
Thank you so much, Mirzad, for the super interesting presentation. I don't see any questions yet in the chat. If you have some, or in the Q&A, if you have some questions, please put them in now. Mirzad can also answer them, I guess, whilst the others are presenting. Yeah.
Yeah, I will stop sharing now.
But I heard something.
I said I will stop sharing now.
Yes, great. Mirzad, but if there's, since there's no other question, I would have one before we move on. Yeah, super interesting. And you put together like what actors are needed also in terms of data provision from like, the ecosystem that you put up there. I think it's quite clear that this is needed. And for me, the question would be how do you have a picture how we get to that kind of collaboration? I mean, it's clear from a system perspective that it's needed, but what could be the incentives of organizations of the industry, particularly of, let's say, grid operators, to share their data and to contribute to such a system? That would be, yeah, I think that could be challenging from an implementation point of view. What's your perspective?
It's definitely challenging. That's why, and one of the reasons is that, so one of the problem is not only just sharing data with the trusted parties, is that in energy sector especially, we have many regulation. And when we have high regulation, it means that the trust is created for collaboration. That's how the value chains work right now. This is though missing for the AI related part. So to somewhat support this collaboration, we definitely require more of the frameworks and governance that can ensure these collaboration are clearly framed towards what it wants to get. So at the same time, I think that we have some success story for this collaboration to be created. One of the example is the energy data space, European energy data space, that there we are seeing many industries are sharing the data. Now, it definitely requires prerequisite, and that would be also how we can actually have a good data governance there for the data that is being used within the AI governance. And this requires more of a push from regulatory parts to gather this information and set at least the smallest framework that then we can append and go forward.
Thank you so much, Mirzad. And I think we have time for one question. And Ahmed.
Yes, thank you very much, Mirzad, for this interesting presentation. My question is related to the risk profile. When we talk about LLM, I mean the foundation models, sometimes there is a possibility for data leakage when we talk about the privacy and the stewardship of data. Did you can you talk about this more? I mean, do you put it into consideration
So I should first start with this. The part about security, I think you know it also. I'm not an expert in that, but I was very closely for this report working with some of my colleagues. And the way that we approached it was analysis of what if. And to be really, really transparent, we didn't find even one way that we can secure the system.
Okay.
So the point was that, okay, with this level that we are from the Cybersecurity Center at RISE, we can come up with ways of attacking and ways of damaging the cybersecurity. And I think this is the reality that we all know. That's why we start with layering and layering security going forward. And that is why the recommendation was that let's first start with that, not layering afterwards. Let's start and go with that.
Of course, we can discuss it in more details because I'm working with different groups and we are targeting actually this aspect, the security of the foundation models. I think we can contact you if you are available. Thank you very much.
Sure.
Great. Thank you, Ahmed, for the question. And yeah, we have to move on, but there are two questions in the chat, Mirzad, and I think the one was on real world examples and if this has been done successfully already. And I think it would be very exciting if you could answer the question in the chat. There's also in the Q&A, there's also one question in the chat. Maybe you can have a look in terms of time so that we give everybody the same time to present. I would like to move on. Thank you very much again, Mirzad. Super interesting. And we move on actually to the presentation of Karim and Ahmed already. They're working at Natural Resource Canada and CanMed Energy. So we're looking forward to your presentation. The floor is yours.
Thank you very much, Heike, and thank you very much, everyone, for joining. Today, my colleague Karim Nadim and myself, we are going to show you how our team successfully implemented causal reinforcement learning approach for supervisory control of energy-intensive processes. And we are, with the application of heat recovery network. Actually, just to introduce myself, my name is Ahmed Ragab. I'm a research scientist working in Natural Resources Canada at CanMed Energy in Varennes. My colleague Karim Nadim is a research scientist as well, working in the same AI team at CanMed Energy in Varennes. So today, the agenda for today is to discuss the context and the supervisory control challenges, and we will give an overview about our proposed approach with obtained results, and finally we'll come up with some key messages and lesson learning. So as you all know, the optimization of complex equipment in energy-intensive industries is very challenging. And this is due to several factors. One of them is the fast and changing dynamics, the large number of interacting subsystems, variability and large number of operating modes and operating conditions, and also the competing KPIs. And this, as you can see here, these are some examples of the processes that we are targeting. The supervisory, when we talk about the optimization, the supervisory control is the main block for the optimization. It's the first step in the optimization process. So the supervisor, these processes, I mean, the complex equipment in energy-intensive processes are controlled by several controllers. These local controllers, each of them wants to achieve its own local objectives, but at the same time competing with the other controllers. And at the end of the day, the global KPI is not well optimized. So there is a clear need for developing a supervisory control methodology that coordinate between all of these local controllers and make them working cooperatively, not competitively. And the supervisory control scheme can have many functions. One of them is the auto-tuning of the local controllers parameters and the recommendation of the set points that make these controllers working in a smooth way and cooperative way. And I'm going to show you some, I mean, the one use case just to better understand the challenge that we are facing in our projects. So this is a heat recovery network in a thermomechanical pulp mill. The objective of this system is to recover the heat from the hot process effluents to be reused in the process in other process units. And the idea is to enhance the energy efficiency at the end. And it consists of 4 subsystems, and we have diversified complex equipments in all of these subsystems. You have condensers, water tanks, heat exchangers, economizers, and you see how it's challenging. So the objective of the control system here is, in this system we have 59 state variables. We are talking about fresh and hot water flows. We talk about temperatures, pressures, and water tank levels. And we have the steam consumption as the KPIs. These are some examples of these variables. And we have 10 PID controllers. These controllers, the objective is to control the dimming, the water, contaminated water flows to the heat exchangers and the economizers as well, and the pressure of the pressurized scrubber. So this controller, at the end, the objective is to manipulate the set points of this controller and making them working cooperatively to minimize the steam consumption and to increase the efficiency of the overall system. And in the same time, we need to respect some constraints and also taking into consideration some performance degradation phenomena such as the fouling of the heat exchangers. And in response to this need, we have developed a supervisory control methodology based on reinforcement learning as one of the simulation-based optimization approach. And I will let my colleague Karim to talk about this in more details.
Thank you. So as mentioned, we wanted to develop an intelligent, centralized approach using deep reinforcement learning. And the idea here is that reinforcement learning is excellent in solving sequential problems. So the idea of reinforcement learning is that we have an agent that interacts with the process. And here we have a process simulation that was created by CATSIM, which Ahmed has represented in the previous slides. So at each time step, this reinforcement learning agent receives data from the process simulation. This data comprises measured variables such as temperatures and pressures, And this data represents the current state of the process. What is the current state of the process? The agent receives that, and according to this current state, this reinforcement learning agent generates actions. These actions are the set points that we give to the local controllers. This is the supervisory control problem. And in order for this agent to evaluate whether the action it took was good or bad, it receives a feedback from the process simulation, which is the reward. And this reward can represent the steam consumption, which is the main key performance indicator that we are trying to optimize. The agent interacts with this with the process simulation in these steps iteratively until it starts to build a model, an accurate model that captures the dynamics of the process, and it generates a very good control policy. And the process, since the process has nonlinear dynamics, therefore this agent uses neural networks in order to capture these nonlinear dynamics, and therefore this methodology is model-free. It does not require a model. And to apply this reinforcement learning, we developed this agent in Python, and we had the process simulation on CATSIM that was created by the process expert, and these two were connected using Excel. So this, by developing this work, we achieved some very good results. So we were able to achieve a 5% reduction in steam consumption compared to a baseline that was created by the process expert. And this baseline was based on some set points that were done to maximize the heat recovery. So we were able to reduce by 5%. And this work was published in Engineering Applications of AI. And for the interested readers, you can find more details about this approach. But after we did this approach, we also thought about the potential for improvement. So the approach that I just described, it was a centralized supervisory control approach. So we have a single agent controlling the whole system, and this system can have many subsystems that have complex interactions. So what are the challenges that we can find by having a centralized approach? First of all, the complex interactions, like I said, and the scalability. So as the number of subsystems increase, the problem becomes more complex. And also there is the problem of the centralized fragility, meaning that if something wrong happened to this centralized supervisory control approach, the whole system goes to a halt. So after discussions with the mill experts, we thought about creating a decentralized approach in order to further improve the performance. So we developed a multi-agent reinforcement learning approach. And the idea here is that instead of having a single agent controlling the whole system, we have multiple agents. Each agent controls a subsystem, and therefore the problem is cut into different subproblems, making it less complex. But at the same time, these agents are also communicating, and therefore this allows to understand the interactions and also optimize the global objectives. And all of this is done under the supervision of the process expert who can help in defining the training strategy and also getting insights from the training. So for the case study, back to the case study, we now have two different policies, a centralized and a decentralized policies. For the centralized policy, we have the single agent, as we mentioned, and we also have an expert baseline. And for the decentralized policy, we have the multi-agent system. So for the experimental setup, we have the simulation that was created by the expert. We have the sampling time as 10 minutes. So every 10 minutes, we receive data for the current state of the process. And the agents, they change the set points of the controllers every 5 time steps in order to reach steady state. And we train for around 200 episodes, which are equivalent to 1,400 days of operation. And we test on one episode. So in order to train these agents and evaluate them, based on the recommendation of the process expert, we did a progressive evaluation strategy based on 3 stages. And the idea here is that to start training the agents on 3 stages, in each stage, we control more subsystems. So in the first stage, for example, we're only controlling subsystems 2 and 3. And then in the second stage, we add subsystem 4. And in the final stage, we controlled the whole system together. And this was for the expert to also gain insights about the training of the agent and how well it does by progressively making the problem harder and more complex. So let's go to the results of the first stage. So here we are supervising subsystems 2 and 3. And the idea here was, as you can see in the figure, we have those two subsystems. The objective here is to maximize the heat recovery efficiency from heat exchangers 2, 3, 4, and 5. And for the controller assignment, now we want to compare the performance of the single agent and the multi-agent. So the single agent is controlling simultaneously these 6 PID controllers, as you can see them in the figure, simultaneously. While for the multi-agent, now we create 2 agents, one for each subsystem. And the set points of the other controllers are kept constant. And this is just a sample to show what are the state definition for the single agent and the multi-agent. And the idea here is to show that for the multi-agent, the state or the eyes of the agents, they look at a subset of the whole system and not the full system. And that way, the problem becomes less complex for the multi-agent process. And these are the results of the training of the single agent versus the multi-agent. The multi-agent is in blue. And as you can see, the agent here was able to converge to a better policy than the single agent. And here we are actually measuring on the y-axis the heat exchanger efficiency. So the multi-agent was able to increase the heat recovery efficiency of the heat exchangers by 2.2% compared to the single agent approach. In the second stage, we now add a third subsystem, which is subsystem number 4. And this also translates to adding one more objective, which is maximizing the heat recovery of the 2 economizers that you can see in the figure in red, those 2 circles in red. So for the controller assignments, now we add those two controllers to the single agent, while for the multi-agent, now we have 3 agents, each controlling its own subsystem. And again, this is just to show the different state definition. And this is for the results. So here now we are measuring the efficiency of the heat exchangers and also the economizers as well. And the multi-agent here was able to increase the efficiency of the heat exchangers and economizers by 3.7% compared to the single agent. And this is the third and final stage where we are supervising the entire system together, so all 4 subsystems. So now we also add a third objective, which is minimizing the steam flow to the ship spin and the aerator. And these 3 objectives, they translate to minimizing the total steam consumption. So now we have the single agent controlling all 10 PID controllers simultaneously, while for the multi-agents now we have 4 agents, each one for each subsystem. And again, this is like we mentioned before, this is the different states and the different reward functions. And this is the results of the training between the single agent and the multi-agent. And we have actually repeated this training over 10 random seats to ensure we have credible results. And as you can see here, the single agent, the multi-agent, was able to find a control policy that is better than the single agent in less time. Only after around 50 episodes. And this is for the testing. So we wanted to test the results now of the single agent versus the multi-agent and also compare to the baseline. So here in the y-axis, we have the total steam consumption, and this is the total steam consumption over 7 days of operation. And as you can see here, the multi-agent, which is the one in blue, was able to minimize the steam consumption, which is the main KPI of this case study, by 5.3% compared to the single agent and 6.7% compared to the baseline, and all of this without requiring a model of the system. And this work has been submitted to the control engineering practice. It has been accepted and it's currently in press. So you can also read about it very soon. So we are proposing 3 main implementation strategies for this approach. The first one is in advisory mode. And the idea here is that we will let the reinforcement learning agents train or learn by interacting with a process simulation. And then we would deploy this in the industry, in the pulp mill, as a recommendation system. So the idea here is that the operators can choose whether to apply or not the recommended set points that are given by our approach. And in the second mode, this is the control mode. And in this mode, after the agents are trained, we give them full control in the industry, and they can directly and automatically control the set points. And the process expert role here is to supervise and to ensure that everything is working correctly. And in the third one, this is the domain enrichment, and this actually happened during our training. And the idea here is that while the reinforcement learning agents are training, the process expert can actually analyze the data from this training, and then it will give them insights that will allow them to even create their own expert-based control system. And here I'm going to talk briefly about causal reinforcement learning. So this is something here that we have applied to the first methodology of the single agent, and we're looking forward to apply it now on the multi-agent. And the idea here is that during training, the agent in the beginning are exploring different actions. And with time, with the interaction, they start to learn better and converse to good control policy. So what about taking all of this data of the training, which contains the success and failure stories and the success and failure instances of the agent, and try to analyze it using a causality analysis approach and create a model, a causal model from this. This model can actually allow us to interpret the AI, how the AI came up with this control policy, because as we mentioned before, these agents are based on neural networks, which are black boxes. We do not understand how they fully operate. So this causal model can allow us to get more insights on how this control policy works, and it would allow for better prediction of future events. So for the key messages and the lessons learned of this approach, the results we have achieved, they demonstrate that the multi-agent reinforcement learning approach can be a promising one to optimize complex systems. So in terms of its efficiency, it was able to actually understand the complex dynamics without requiring a process model. And for the scalability, when we compare the results between the single agent and the multi-agent in different stages, we can see here in green that the improvement margin between the multi-agent and the single agent increased as we increase the number of subsystems. And that shows that the power and the capabilities of the multi-agent shows more the more the system is complex, and the more the system has more subsystems to control. In terms of resilience, we can say that it can be more resilient than the single system because it's based on multi-agents. So if one of the agents fail, the other agent can still work and compensate. Of course, reinforcement learning can have some challenges, which are also opportunities. So the reward definition, which is what guides the agents to perform and understand the process, it can be challenging to define. However, the advancements of reinforcement learning, such as reinforcement learning with human feedback and transformer-based reinforcement learning, can be used to overcome this challenge. Also, the hyperparameter optimization, which also there are advanced optimization algorithms that we can use. We want to emphasize that this approach is a human-centric AI approach, meaning that the process expertise is indispensable in terms of problem understanding, supervising the approach, the state definition, etc. So we cannot work without the process expert. We need the process expertise. It's very important. However, the AI can help significantly reduce the expert's efforts. We want to work hand in hand. And for the deployment of the tool in advisory mode, as we mentioned before, it can be applied as a recommendation system, and this would allow to avoid the intrusion of the tool in the existing control system, which can help in its acceptance and implementation in the industry. So thank you all. This is our contact if you want to contact us, and of course if you have any questions.
Thank you so much, Ahmed and Karim. Also a very interesting approach that you're taking here. And I think there's one question in the Q&A, and I think you've mentioned it to some extent just now, but maybe we can dig a bit deeper. The question from Leo was if you have some first feedback from the industry, particularly on that control and advisory mode. Like I think it's a clear assumption that the control mode might not be so favorable by the industry, but is that the case? Have you had direct exchange and feedback on that?
Yes. For that, that's why we presented first the advisory mode, which is the more reliable mode in this case. So the approach can work as a recommendation system, and this can work for any system that has safety risks that is critical. The control mode can work in other systems where there are no clear risks. So we recommend working with the advisory mode, which would allow the operator the full control as it is, and the AI will just help to analyze the current state of the process and recommend some control points that will some set points that will actually improve and enhance the desired KPIs. The operator in the end can choose whether or not to apply these set points.
And also, if I would add to what you mentioned, Karim,
Sure.
this simulation is based on the real use case from the industry, from one of the departments in Eastern Canada, and the process expert working with us, who is in charge of developing this simulation, based on the discussion with the male staff, and in fact, these are like potential impacts. What we identify, what we achieve in terms of impacts, steam consumption reduction, but we are still in discussion with the mill to discuss these different possibilities for the implementation.
Mm-hmm. Thanks a lot. Then there are two more questions. So the first one is if you're planning to extend the work towards methods that allow some changes within the system. So let's say if we're talking about electrification, will it be possible to implement these kind of process changes within the learning, like that it's not that you don't have to start from scratch, but can see what kind of process learning would.
Yeah, that's a very good point, but very good question, because our approach is incremental and it's generic. I mean, once we add any subsystem, so we are incrementing and adding other agents that it's a kind of modular approach. So it can be extended to other subsystems in the middle. Yeah.
And also adding to that, that's a very good answer. But adding to that also, that reinforcement learning in general, it's good in working with uncertainty. So it can do a good job dealing with novel events, so events that it had not seen before. And we have previously tested that with some scenarios that the agent has not seen before, and we tested whether the agent would be able to actually react better than the baseline to this approach. And to our surprise, the agent was able to actually still react to these events, even though it has not seen it before during training. Mm-hmm. So it shows that these approaches or these methods can be generalizable and can work with different systems.
And this is actually due to the fact that we add the causality, because when we add the causality to these agents, we support the reasoning part. So it's not only just sampling and optimizing, but it does know why achieving this optimized KPI. So this is very important. The causality, this is our belief. The causality should be integrated to the reinforcement learning.
Thank you very much. And then there is one more question, and I'm asking for a quick answer because I know it's for a quick answer. And also to the people attending, it would be great if you use the Q&A function rather than the chat, because then the speakers have a better overview of the questions that are targeted towards them and can also answer you later without having a complex chat to check. So please use the Q&A function. But for now, the question is to which extent, like the training of these models takes a lot of energy. We all know that. To which extent you're considering the trade-off between the energy it uses to train the models versus what it saves, and I assume it depends a lot on what you are optimizing and what potential is there in the savings.
No, that's a very interesting question, and this is actually because I understand your point, because there are many conceptions about the energy consumption regarding the AI models and foundation models, but we are not in this. I mean, we are using simple agents that can be trained on. This agent, for example, take like 1 week to optimize. So imagine we are running this on our laptop, and this is in fact can consume the same energy that like if you are preparing 4 sandwiches using your toaster, exactly the same. But we are not talking here about large language models that are consuming a lot of energy. It's completely different. Yes. We are exploiting AI as prescriptive modeling capability to optimize and to prescribe policies, control policies. Very simple models used on our laptops, and it doesn't consume a lot of energy. This is short answer.
Yeah, thank you very much for pointing that out. I think that's super important to make this point, because I mean there's a lot on how much energy AI needs, but it's always the AI, and all the kind of models are put into the same melting pot. So of course we have very different functions that this can perform, and the differences in savings are quite large.
And also the difference between AI as API. I mean, like ChatGPT and this, that one prompt can consume a lot, because it's the concept of data centers. It's completely different than what we are doing. We are using AI as a computational modeling framework that help us to achieve energy efficiency.
Yes. Thanks a lot. And Heiko put already on his camera, which is a good sign. We should really switch over. Thanks a lot, Karim and Ahmed, for your presentation. And there's one more question for you on the time it takes to train. So maybe you can have a look at the Q&A and answer that one in writing. And yes, Heiko from Etalytics is presenting on the research project KI, so German for AI, for ETA, and we're very much looking forward to the real impacts that you are that you promise in the title. So we're excited to see.
Perfect.
The floor is yours.
Thank you very much. A super fascinating talk that I just heard, and I think it's kind of my talk will go in the same direction, so it's actually quite coherent. We stay on topic. So I will share my screen. So I named the talk "Research Leads to Real Impact," and I want to explain that basically in 2 ways. So the first way research led to real impact is that Etalytics exists at all. So we are a spin-off from the Technical University of Darmstadt. Darmstadt is a town close to Frankfurt. And so we are basically born out of research projects. And the second is I want to use the research project KI for ETA, so AI for energy efficiency, basically, to give an example of what we have developed. So I want to start to give like a quick summary of what Etalytics is doing at all. So we are a software company, and we are also focusing, just like we heard on the talk right now, we are focusing on optimizing, like the optimized control of systems. And in our case, we are focusing on supply systems. So supply systems are our machines that are providing factories with heating or cooling, pressurized air, ventilation. So everything that is not directly connected or directly inside of the production process, but like the secondary machines around it that are necessary to run the production at all. And these supply systems, you can find them, like I said, in all production facilities, in data centers, chemical industry. So it's quite a broad technology. One example of that is what you can see here on this slide. So this is a small research factory that is on the campus of Technical University of Darmstadt. And let me just quickly jump here. I hope you can see that I'm now sharing my browser, because there is like a small walkthrough that I want to give you. Because here I can show you how this research factory looks like. So here you can see the building from the inside, and you see there is like a real production line inside. And basically in the research project that I will introduce on the next slide, we were able to use all of this equipment and play around with it without any risk of damaging some real equipment. So it was like the perfect playground. We could really control all these machines, either in the production line and also the supply machines that are in the basement of this factory. So it's all a self-contained system here. So in the basement, you will find heat exchangers, combined heat and power units, gas boilers. There's thermal storages and so on. So we found everything here that we needed to do a great research in this AI for energy efficiency research project. So what was the research project all about, and which role did we play as Italytics? So the research project was quite large. It had like a lot of involved partners here, and a lot of, let's say, part projects and work packages. So it is a little bit hard to compress it down, but I tried to do that with this slide. So the core you will find here in the middle, where the real factory is displayed. And the idea of the project is there is the factory and it is operated in a certain way. And then there is the way it could be operated the most efficiently. And there is a gap between these two ways. And the idea of the research project is to address as many of individual points as possible with digitalization and AI to bring the operation of the factory closer to its optimal operation. And this was done using like a closed loop approach. So you see there's like the cloud here, which contained simulations and models of the real systems inside of the factory. And then we were using these models, for example, models of the control system, so models of this supply system, to then find better control strategies and controlling them. So actually, we also in this research project we also used reinforcement learning for that. So this was one of the approaches that were tried. But there were also many other things tested out. So there was the use of how AR glasses can be used to get a quick insight into the energy flows inside of a factory, or scanning, let's say, PDFs of the electrical infrastructure to automatically detect the largest consumers of electrical power. There was also like robots running around scanning for pressurized air leakages, since these are very costly. And we also looked at, okay, if you extend the factory, like if you look outside of the factory, there is also the net. So we were looking at a sector, like combining it with the electricity grid, and also bidirectional charging of EVs. So we actually, in this research project, were able to buy an electric vehicle and use it for bidirectional charging. So quite a grand scheme that we had in this research project, and the role of Italytics was basically to provide the platform as like the digital backbone for the connection between the data connection of all the machines, and then doing optimizations and writing it back to the real system. So we're like a little bit like the spider in the middle of the net, trying to make everything interoperable, connecting the necessary components for the different use cases. There's also, since the project is already over, you will find the public final report in this link here. I'm not sure if the slides are shared afterwards, but these slides can be shared. And there's also a link to a summary video that shows the some results, some exemplary results from this research project. I just quickly want to mention the partners that were involved. So university partners, institutes, the German Research Institute of Artificial Intelligence, which is quite a large organization, some well-known industrial partners, and actually multiple partners that were building energy management software like Software AG, Ökotech, and also us, with the addition that we are also like actively controlling systems. And additional associated partners and subcontractors were active in this project. So here, our role, I already explained that, what's written on the slide. So we were leading the sub-project 1, which is about the smart energy management platform, like the spider in the net. And we were integrating, we were building up data infrastructure and enabling connectivity in this project. So what did this lead to? Like, what is the real impact that I'm talking about? So this project really helped us to master the symphony. And what I mean by that is all these individual systems that we also heard about in the talk before and that I also explained right now. So if we have a cooling system, we have multiple cooling towers, there's heat exchangers, there's a lot of pumps, there's valves involved. And all of this typically is controlled with like individual control strategies, and synchronizing it to work together in the most efficient manner is quite complicated to do. The work that we could do in the research project enabled us to build up the infrastructure to think this all together and really optimize the whole system at once with a centralized optimization approach. And this is the conductor that you can see here, harmonizing how all the individual systems are operated. So we have a centralized operation approach here. So why is this difficult to do? I just mentioned there's many systems involved, and there's complex topologies that we typically see in the supply system realm, which means that if you have many systems, of course, there's many decisions that you have to find of which combination of different set points is the most efficient one in exactly this situation that you are in. And also there's diverse interdependencies. So usually, for example, cooling systems are highly dependent on the weather conditions and also on the load that that they have to cool. So there's a lot of interdependencies and dynamic influences, like if you have fluctuating electricity prices or fluctuating weather or load conditions, all of this needs to be addressed in the optimization approach. So how did we approach that? We have a complementary or not complementary, we chose like a different path to the reinforcement learning path that we just heard about. So our approach is based on mathematical models at its core, which means we look at the real system, which consists of multiple individual systems and or components. And we have like a library of digital components that we then take, and we can tune those individual components with real data from the system to behave as closely to the real system as possible. So this is like the training aspect of this mathematical individual model. What you see here is a symbol of real data points and then a model in the background that is kind of fitted to these real data points. So then we know that this individual component closely resembles the behavior of this real system component. So once that's done, we do that for all of the components of the system, which then gives us a real digital twin that is the basis for our optimization approach. And at this stage, we also take into account third-party data like weather, energy market, and so on. And then we can finally close the optimization loop. So we read the current system state, we put our digital twin into the exact same system state that we find in the reality, and then we solve this model for the best possible set of set points. And then we give these set points back to the user. This can either be done as suggestions, or we actually write to the real systems. So that's the basic concept that we follow, and this is quite a flexible concept because it allows us to tackle multiple systems, like I said, heating, cooling, since the approach always stays the same. So there already have been quite some success stories that we were able to achieve with this approach, and the product that we built out of that, as like I said, a spin-off from university. Since 2020 was our spin-off date. So this is one example for a data center. A lot of our customers right now are data center operators, since this this area is growing a lot. The exponential growth of the data center capacities. And so here we were looking at a cooling system. We were able to achieve over 40% of savings on this cooling system that we looked at, with quite significant energy reduction. And since we don't require any changes to the real physical systems, but just a different way to how to control it, the amortization period in this case was less than 1 year. And yeah, of course, getting positive feedback for that was very nice. But actually, the approach has also some other benefits, this digital twin approach. So the first one I already talked about, so which is like actually lowering the energy consumption, since we can more efficiently operate the individual systems. The second one is, this is an example from a data center as well, where it's very important to cool the server rooms with a reliable temperature. And with the old rule-based control strategy, you can see that it scatters quite a lot around the target value. And with the blue strategy that is coming out of our optimization approach, we were able to control these temperatures much more precisely. And additionally, which is another nice side aspect of working with digital twins, we can also kind of do condition monitoring approaches with this, because we see when suddenly one of the real world components is deviating from the tuned mathematical model of that component. So if there is a sudden deviation, we can detect that, and we can, and this hints at some error from the real system. So for example, what we've seen is that the filters of cooling towers were clogged, and we could see that in the data before the usual maintenance schedule happened of the customer. So yeah, we try to put that all together into one product. Our main product is called the ETA1 platform, and this is also what we were able to, let's say, expand in the AI for efficiency research project, let's say. And another thing that we can do with this approach is we can actually compare multiple components that we could have used in the mathematical model, and we can play through historic data, like an historic year, let's say, and what would the energy consumption have been if we would have used that pump instead of the currently implemented pump. So we can simulate that, and we can kind of do retrofit analysis with the approach that we have chosen. So I just wanted to mention that our main field that we are focused on is like reducing the energy consumption, since this has like immediate financial impact also on the customers. But it has like nice side effects that we are also now expanding on. And all of this, like all this capability, is heavily dependent on interconnecting the models, also interconnecting different data sources, like connecting to all these different customer systems. Of course, they have different technical protocols that we need to address and so on. So for all of this, it was very helpful to build a generalized scheme, a generalized data scheme inside of the research project. Since this was also mentioned in the talk before, of course we are also faced with, okay, how do we integrate that into the real customer settings? And there's at least from our side, what I can report back basically. There is what works good for us is a 3-stage approach, which is the first one, human in the loop. So we kind of just show the optimal set points that our optimizers find, and we can just display them, and the experts of the customers can look at that. We can also expand the freedom of the operating freedom that we have. So instead of switching the pump from 70 to 80% only, we can expand that to between 50 and 100%. So that's the first stage. The second stage, we usually switch on the optimizer for some time, then switch it off and switch it on again and off again. And then we compare these two situations, like we can cluster it, and we see, okay, how large were the savings really in similar conditions. So this is like the proof that it actually works. This is where the 10 to 40% energy savings usually are shown. And then the last stage is going to the full control. The optimizer is running all the time and is operational. And we also have to make sure that it always stays safe, everything. So for this, we use fallback mechanisms. So basically like an extra check that the signals that are provided from the ITA1 platform, from the optimizer, are only used if everything goes according to plan. Like if anything small is falling apart, the old conventional control is back in control, basically. So these are, since then we could expand to more verticals. We have like data center customers, automotive. So for example, we did cooling use case for Stellantis, or air conditioning use case for Stellantis, or cooling use cases for data center operators. And we are gathering more use cases every month. And are now 70 people and expanding still. So these ideas that we first looked at, but that we could expand on in the research project really paid off. And we are now using that knowledge to expand our business model. And with that, I'm at the end of my talk, slightly ahead of time, and I'm looking forward to your questions.
Perfect. Thank you so much. Yes, and that was really real impact. So very, very exciting, I think, to see where this where this ends up, and also to see where the research projects can really support such a completion, let's say, from the theory into the practice. I think that's a very prime example for that. I don't see any questions yet. For me, maybe as long as there are no questions in, I would have one at least. You mentioned, for example, that with the mathematical models, you can see like if the components behave differently than what is expected of them. You can see that maybe something is not running as smoothly, and using also as predictive maintenance. So, but that already, I would assume it already requires a quite high level of sensoric data in the different in the processes that you are looking at, right? I mean, maybe you can say something about that, like the level of optimization or sensoric data that is needed for your approach to work.
Yep. Yeah, that's true. I mean, this is a data-based approach, and actually for this to work, we need to read quite some system data, but usually, like in most cases, the available data is there because the companies have energy management systems, or at least are monitoring also the energy usage that they have. And for that, they already need like a lot of these data points that we would require. And additionally, since we have this modeling approach, we can kind of fill the gaps also with the models. So sometimes if you know the temperature of a heat exchanger on the one side or the mass flow, then you can calculate the mass flow on the other side, even if there is no sensor. So this is like the second best option, of course, but we can like bridge a lot of gaps like that. And typically in the beginning, we do a check, like is the project feasible at all or not? And there we also check at the data availability, and sometimes not so many additional sensors are needed, and then they can just be retrofitted.
Okay. Yeah, great. Yeah, I mean, it's also interesting because we have a huge debate in Germany, at least on the question of energy management systems and for whom they should be obligatory and for whom not. And I think, yeah, that just it's also clear that the energy management as such does not save the energy, but particular things like that can build up on that, like your approach is then what brings the savings, of course. I mean, just having the data doesn't mean yet we have savings, but it opens so many additional options that were not there before. And I think it's an important point to make when we are now also discussing about thresholds for which audits and management systems are needed. Thanks a lot. Then there's one question from Mulut.
Yes, thank you for this excellent presentation. You mentioned that you went to full control. And my understanding is the systems that you are talking about, I mean, your applications are quite, I would say, simple. Do you think that the approach will apply to complex industrial systems like refineries, pulp and paper mills, and so on? Do you expect some challenges or?
Yep. So we have like a broad range of use cases that we see. Some are quite simple and some are very complex. In principle, this approach can be used for all of these because all we do is like put together more and more complex models. The problems that can arise there is that, of course, like we solve these models iteratively, for example, every 5 minutes or every minute. So if it's a larger, more complex model, it takes more time for the solver to solve that model. And we need to stay under 1 minute, basically. So sometimes there's restraints, especially like, for example, for a lot of data center cases, we solve for the next time steps. But if there's a lot of flexibility in the system, so if you have, for example, large thermal storages, then the optimizer has to look into many future steps, also extending the complexity of the optimization problem that has to be solved. And then it becomes tricky. But in principle, this approach can be applied to anything. And yeah, we have seen quite complex use cases that we can tackle with this.
My point is, you mentioned at a certain moment that you can use some simulators like energy balance and stuff like that. But when you are going to very complex process, it's very difficult to have access to such simulators.
I mean, we built the simulators ourselves because we use this mathematical model approach, and we have like a library of individual components. And actually, these components are like repeat themselves again and again and again because these are the supply systems are kind of I'm looking for the English word here. I don't know. It's like this technology can be used in many different places. It can be used in a factory, but also in a data center. So we see again the same systems again and again, which helps spread the approach to multiple areas.
Okay, thank you very much.
Okay. Thank you so much for the presentation. A very interesting one, and excited to see a project presentation again soon on in our conference. So we move on to our last speaker, which is Michael from the University of Southern Denmark, and he's presenting on also a very practical approach of AI in industry. Michael, the floor is yours.
Yeah, thank you. Oh, I think.
Yes.
Yes.
Yes, now we see the full mode. Yes.
Yes, thank you so much. Hello everyone, I'm Michael from SDU Center for Energy Informatics. Today I will present our project Decode. The full name is a data-driven best practice for energy efficient operation of industrial processes. Before presenting the project, I will shortly introduce my center and me. We are from University of Southern Denmark in Odense, which is a city in the center of Denmark. And our center's research focuses on developing digital solutions for increasing the intelligent use of energy within the 6 interconnected teams, from smart buildings, smart cities, to smart industries or smart energy systems. I am the postdoc researcher in our center, and my research focused on industrial digitalization and developing the AI and data science models to analyze the energy efficiency and energy flexibility in industrial systems. Now we move to the project. This is the agenda for today's presentation. I will firstly introduce the overview of the project, then move to the motivations, objectives, and then next I will introduce the conceptual framework guiding the project and the work packages. Finally, I will introduce the outcomes of the projects, including the developed tools, models, algorithms, and some results. This is a summary of the project. This is a 4-year project started from September 2022, and the project manager is Professor John Grisma. We have 4 industrial partners, the company Vanderbilt and Lactosam. They are the 2 industrial companies provides data for case study and the system implementation. The company Philomine, which is a data management company, they will work focus on to develop the an energy cloud platform to visualize the data and also work on the data management. The company Innovatech, they are the IoT company which help us to install the sensors to collect the energy data and the industrial operation data, and they also manage the sensor data using their IoT systems. Next, I will introduce the motivation and the background of the project. In Denmark, we have the targets of reducing 70% of the CO2 emissions by 2030 and achieve the climate neutrality by 2050. So the energy intensive manufacturing sector should achieve rapid CO2 reduction and deep energy efficiency. As a result, it's very important to explore the digitalization and the data-driven technologies that can analyze the energy efficiency and improving the energy flexibility potential in industrial sectors. However, despite the extensive sensor data and automation, in the real-world production plants, they already collect a lot of energy data and the operational data, but they didn't utilize them a lot. They lack the integrated platform and system to visualize the energy data to analyze the energy consumptions of the industrial processes. And they may also mainly rely on the local heuristics rather than you utilize the data-driven optimization. And from the scientific perspective, now there's no scalable framework that can combine the high resolution industrial data with the advanced AI and the machine learning models to achieve the decision-oriented performance benchmarking. Therefore, this project aims to develop an energy IoT cloud platform which combines technologies of IoT, big data, edge computing, also artificial intelligence and digital twin technologies to support the production industry's evaluation and adoption of the best practices for optimal operation of the entire production plant. The IoT-enabled edge computing infrastructure with energy smart meeting and sensors can be used for the process monitoring, the data collection, and the visualization. And the energy cloud platform can visualize the energy data and also the machine learning results for the industrial consumers. This is a conceptual framework of this project. In this energy IoT cloud, it builds upon the edge computing based data logging concept from the Innovatec and integrates it with a newly established IoT cloud framework developed by Innovatec and fellow minded together. These two companies help us to install the sensors, manage the data, visualize the data, and our department focus more on the scientific research to provide the AI and the machine learning or digital twin solutions to analyze the energy and operational data. These are the working packages of this project. There are 5 technical working packages in total. Working package 2 and 3 are managed by the companies Philomine and Innovatec. They installed the sensors and collected the data. And in working package 5, we use the 2 companies, Value Beer and Lactosan, as the case studies. We analyze the energy data and the industrial processes data with various statistics and machine learning models, or also some large language model framework to provide the decision-making support. And in one case study, we also developed the digital twin framework to test the data analytics results to validate the framework. Then all the results, including the data visualization platform, the machine learning, the digital twin, they will be integrated together as the energy IoT cloud platform. These are the 2 case studies in this project. Vanillabien is one of the largest foundries in Northern Europe, and Lactosan is an international Danish producer of cheese powder. They are both the energy-intensive sectors in the in manufacturing and the food industry. Next, I will introduce the solutions and some results of the project. And because we have worked over 3 years on this project, we finished most of the work and developed some platforms and published some scientific papers. Till now, our solution includes an energy cloud platform developed by a fellow mine, and a digital twin framework and a multi-agent simulation developed by one colleague from our center, and then an AI-driven decision support framework, which is the contribution of my PhD thesis. First, I will show you the energy cloud platform. In this platform, we can showcase the energy consumptions to the industrial consumers. In this demonstration, we use the lactosan, the cheese producer, as a case study. Here, we can visualize the average energy consumption per kilo for each order of the cheese productions. And we can also visualize the sensor data, the real-time sensor data to the consumers, so that they can see if there's some strange operations that they can interrupt to solve. Next, for the other case study, the foundry, we focuses on the induction furnaces, which melting the collected metals and alloys, because it accounts for about 60% of the energy consumptions in a foundry. Before introducing the solutions and the results, here I briefly introduce the industrial processes of a foundry. The process begins with sorting and preparing the melting materials by scraping the metal collected from the scrap piece. And then they are moved into one of the induction furnaces and heated to the target temperature. Once the melt reaches the specified temperature, it's transferred into a preheated ladder. When the ladder will transfer the melt into a holding furnace. Then the forming stage is carried out in diesel machines. The melt is withdrawn from the holding furnace into a preheated ladder, where further alloying may be performed to meet the customer specified the requirements. Then they are poured into the molding equipment. For example, the sand molds in this case to produce the primary casting. Here is a digital twin model developed with analogic software. In this case, we use a digital twin to create a data-driven virtual representation of the industrial processes. And we use multi-agent simulation models to integrate the multiple elements in the industrial processes to capturing how the local decisions and adaptations leads to system level behavior. This is a logic and the implementation of the digital twin framework in the analog logic. In this work, two scenarios are simulated. One is a baseline from the historical data, and the other is the optimized operations. Here, we use the time series k-means clustering and the multi-criteria decision making to select the energy efficient operations and simulate it as working processes and compare it with the baseline. The results show that about 20% of the electricity cost can be saved, and we can also save about 15% of the carbon cost. The digital twin and the multi-agent simulation work have been published in these two paper, and for more details, you can contact my colleague Daniel Anthony Howard. And then finally, I will introduce the decision support framework for this project. It's developed by myself, and which is a key component of my PhD thesis. You can scan this QR code here to view and download my PhD thesis. It is an end-to-end, human-centric, and explainable decision support framework. This framework starts from the data collection and acquisition. Then we examined the quality of the real data and perform the necessary data quality diagnosis and data pre-processing to ensure a higher quality data for the further data analytics. Then in module 3, the time series clustering algorithms is performed to analyze the melting process in the induction furnace. After the clustering, some necessary post-hoc statistical analysis and explanation are performed to ensure each stage of the decision support is explainable. Then in module 4, it is one of the most important stage in this framework is the causal reasoning and inference, because we should not only know what is the efficient and inefficient operations in industrial process, but also we need to know why and which variable cause the energy efficient and the energy efficient. Here, I did develop a pipeline to discover the causal structure within each cluster, and then verified and validated the causal structure. You use statistical models, and then use a sharp-based root cause analysis model to analyze which variable are the root causes of the energy efficient and or some key operations. Finally, I developed a large language model based framework to generate a report based on the data analytics results to support the decision making in the real world environment. No, it's 20
Michael,
minutes.
a quick.
Yes,
Yeah.
it's 20 minutes now. I can quickly show the results.
This would be great, because we don't want to lose people before you're coming to the results section. So maybe you can quickly go to the results. And
yes.
Okay, close.
This is the data in this case study, and this is the first temperature in the induction furnace. Each cycle from the temperature very low to the highest temperature and the cooling down is the melting cycle for the induction furnace working cycle. Here I develop a data characteristic understanding framework to analyze the data quality of real sensor data. And I also develop a deep time series clustering algorithm to analyze the melting temperature profiles in the industrial processes. Here is the results. All the temperature profiles are clustered into 7 groups under different operational modes. This is the pipeline of called the inference and the reasoning. Here is the results. We can see that in different clusters, some called links are similar, but some are different. We conduct some intervention in experiments to identify which are the real root causes of some key variables, such as the temperature, the energy consumption, and the weight of the metal in the furnace. Finally, I developed the multi-agent multi-model large language model framework to automatically interpret the scientific and data analytical results to the textual knowledge, and try to use large language model based on their global knowledge to provide the real world decision making recommendations based on the data analytics results. Here are the large language model generated recommendations. For more details, you can download the publications here, and of course, you can directly download my PhD thesis and all the results and the theoretical framework. They are in my PhD thesis. Yes, thank you. If you have more questions, we can discuss it now.
Thank you so much, Michael, for the presentation. Also a very interesting one, and a lot of detail that has flown into the work. I don't see any questions currently in the chat, but the people also have your contact details, and in the matter of time, I hope it's okay if we come to the closing. Thank you very much. Thanks also to all the other speakers for the super interesting presentations. I hope to the audience that it gave you a good introduction, or introduction and deep dive at the same time of what is currently happening in the various research research projects on AI in the industrial sector. Yeah, thanks a lot for switching on the cameras again. Thanks for staying until now. We know it was a long webinar this time. We'll stick to the 3 presentations next time again, but we had so many interesting presentations and projects here that we wanted to bring together. Thanks a lot for staying in until now, and have a good evening, afternoon, morning, depending on where you are located. Thanks a lot and goodbye.
Thank you very much.
Thank
Thank
you.
you very much.
Thank you.
Bye.
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 Bye-bye.